Alright, so we start with two positive integers a and b, and we define their greatest common divisor, or their GCD, to just be the largest positive integer that divides both a and b. So we use that notation, GCD of a comma b, for that value. The GCD of 18 and 30 is 6. It's the largest positive number, the greatest positive number that divides both 18 and 30. And when the numbers are small, the greatest common divisor isn't too hard to find. We can just factor and go from there. We say that two numbers are relatively prime if their greatest common divisor is 1. So when we're talking about relatively prime, we have to be talking about two values at a time. And we're going to learn about what's called the Euclidean algorithm as a way of finding the greatest common divisor of two numbers. And the Euclidean algorithm is fairly straightforward and simple, and it's very efficient if you program it into a computer. So here's the statement. We let a and b be positive integers, and then if b divides a, then of course their greatest common divisor is b, but otherwise there exists a decreasing sequence of positive integers, so r1 through rn, that are remainders when we do long division, so perform the division algorithm repeatedly, and eventually when we do division enough times, we finally get down to a remainder of 0, and that last remainder term, r sub n, is the greatest common divisor of a and b. So you might notice that the remainder term shifts over each time, takes on the roles of a and b. So it's not really going to make much sense until you see an example, but at that point I encourage you to come back and actually watch again, because or read through the statement. It will make more sense then. We're not going to prove it now, but I'll just point out the key idea is that if a is less than b, then we can say the greatest common divisor of a and b is the same as the greatest common divisor of a and b minus a. So we can replace the larger number with some number obtained by subtracting multiples of the smaller number. And it's not going to change any of the divisors. So the greatest common divisor of 18 and 30 will be the same as the greatest common divisor of 18 and 12. That 12 was obtained by just doing 30 minus 18. And we can do the same trick again. We can replace the 18 with 18 minus 12. That leaves us with 6. Then we can replace the 12 with 12 minus 6. The greatest common divisor of 6 and 6 is 6. So that's the idea. But when the numbers are bigger, you've actually got to pull up the division algorithm. So the Euclidean algorithm says just repeatedly apply the division algorithm until we can't divide any longer. And we're not going to lose our common factors. So as an example, we're going to find the greatest common divisor of 42 and 96. So we put 96 on the left as the larger number. We perform the division algorithm, and we see that the remainder is 12. All right, then we're going to take that 42 and the 12 and do the division algorithm again. And in that case, the remainder is 6. Then we're going to use the 12 and the 6. And in that case, we get a remainder of 0, and because the remainder is 0, that means that our greatest common divisor is 6. And that's easy enough to verify when the numbers are this small. As another example, to find the greatest common divisor of 58 and 36, we put the larger number on the left, so 58 is 36 times 1 plus 22 is the remainder term. Then we do the division algorithm again, but we'll use 36 and 22. In that case, the remainder is 14. So now we'll do the division algorithm with 22 and 14. The remainder is 8. With 14 and 8, the remainder is 6. With 8 and 6, the remainder is 2. And then finally, we get a remainder of 0. So the greatest common divisor of 58 and 36 is this last non-zero remainder, which was 2.